Okay, so we were just started this section on characters and the character space. Now, so far we'd looked at invertible elements. And so we only needed to define the inverse on one side rather than two because we're commutative. And then the inverse of the inverse is the inverse. And you have the invertible group in A because it forms a group under multiplication. And then I've given you some examples. And when we took a compact Hausdorff space X, and then we looked at C of X, which was the Banach algebra of continuous complex valued functions defined on X, then the invertible elements were just those which didn't take the value 0. And in those cases, you can just do 1 over the function. So that's no problem. And I said the same was true for R of X and A of X, and not for P of X. This is not invertible. This is in P of X, of course. If you put alpha in the whole, it is invertible in R of X because 1 over Z minus alpha will be a rational function. So as long as alpha is not in X, you can do 1 over Z minus alpha in R of X. It's in R naught of X, but it's not in P of X. For such alpha, let's put an alpha in there. Anyway, so that's some discussion of invertible elements. Now, here, Theorem 2.2, this is what really gets you started in Banach algebras. This doesn't work in normed algebras, but it does work in Banach algebras. And the idea is that you can define 1 over 1 minus x by this series as long as the norm of x is less than 1. So let's have a quick think about that. First of all, it's a Banach algebra. So remember, the norm of AB is less root of norm A, norm B. So the norm of x squared is less root of norm x times norm x. Right, taking A equals B equals x, which is norm x all squared. And similarly, norm x cubed less root of norm x all cubed, etc. So basically, what you get is norm of x to the n is less root of norm x raised to the power n. There's an x to the 0 in here. X to the 0 is 1 by convention. And now this looks like a geometric series here, which you would expect to add to 1 over 1 minus x, except that we're dealing with elements of a Banach algebra, so you want to make sure this is actually correct. So let's see the proof of Theorem 2.2. Well, first we look at that series. Since the norm of x to the k is less or equal to norm x all to the k, we have the sum from k equals 0 to infinity. Just move that down a bit. Sum from k equals 0 to infinity of the norm of x to the k. That's less or equal to the sum from k equals 0 to infinity of norm x all to the k. And that smaller than infinity is just a geometric series because norm x is less than 1. So you just use a geometric series. So, since the sum of the norms converges, and because we're dealing with a Banach space, a Banach algebra in fact, so since A with norm is complete, the series sum from k equals 0 to infinity of x to the k converges in A to some element which we'll call A, say. But now, let's look at what x times A is. X times A is x times the sum from k equals 0 to infinity of x to the k. And because continuity, because multiplication is continuous, that's just, you can bring the x inside, and that's the sum from k equals 0 to infinity of x to the k plus 1. That's because multiplication is continuous. And so you can bring a product multiplication by an element of the algebra inside the sum, which is equal to the sum just re-indexed. That's the sum from k equals 1 to infinity of x to the k. And now you look at 1 minus x times A is equal to A minus xa, and you see there's only one term left over, which is the first term, which is x to the 0, which is 1. So 1 minus x is invertible, and it's got this formula for the inverse. Oops. Sorry, sum from k equals 0 to infinity of x to the k. Which is 1 plus x squared, and so on. Oh, and the last part is just rearranging that so that the rest is then if this is a different element A, if A, this is not the same A as above, if A is in A satisfies the norm of A minus 1 is less than 1, and I wish I hadn't used A above now, this is a different A. The norm of A minus 1 is less than 1, then 1 minus A minus 1 is in inv A by above. Though in fact 1 minus A might be better. let me use 1 minus 1 minus a. You can take x equals 1 minus a this time. That's why it's a different a from, it's not the same a as before. I.e. a is invertible. So if you're within norm 1 of the identity element 1, then you're invertible. And that's going to play an important role. Now, this is very much a Banach algebra result. It's not true in normed algebras. We use the fact that it's complete to justify the claim that that series converged. If it's a normed algebra, that series doesn't have to converge in the algebra, in the normed algebra. Okay, so now, finally, we can tell you what a character is. It's a non-zero multiplicative linear functional, or in other words, a linear functional that preserves products, but it mustn't be the zero linear functional because that's boring. So obviously the zero linear functional does preserve products, but it's not interesting to us. So we only want a non-zero one. And since mostly we'll be working with algebras with identity, it turns out that under those circumstances, if you're multiplicative and not the zero functional, if you're a linear functional that's multiplicative but not the zero functional, then you can prove that phi of 1 must be 1. I won't do the whole thing here, but let me point out that phi of a is going to be equal to phi of 1 times a is equal to phi of 1 times phi of a. So whatever phi of a is, and these are complex numbers, remember, so whatever phi of a is, phi of 1 times phi of a is still phi of a. Okay? Now phi of a is 0, that tells you nothing. But if phi of a isn't 0, then phi of 1 has to be 1. So as long as it's a non-zero multiplicative linear functional, then it's got no choice. It must be that phi of 1 is 1. And here's a useful fact. Now this is back to the product space. This is like something we had before. If you're a linear, what we had before was, remember, the linear functionals were closed in the product topology, and that was an exercise for you to check. Well, it's also true that the multiplicative linear functionals are closed in the product topology. So let me just remind you that A cross that was the algebraic dual. That's the set of all linear functionals. And this is similar to the fact that A cross is closed in C to the A. So earlier we mentioned that the algebraic dual is closed in the product topology as a subset of C to the A. And now if you just throw in being multiplicative as an extra condition, it's another condition that keeps you, you stay closed. So I won't prove that, but you can check that as an exercise. So that's for A being unital. By the way, that's not true if A isn't unital, unfortunately. But we'll mostly work with unital algebras here. The reason you need the unital one is that in general what happens is the multiplicative linear functionals are closed. But it is in general possible for the zero functional to be in the closure of the non-zero ones. But that doesn't happen if you've got an identity element around, because all the non-zero linear functionals will take the value 1 at 1. And that will be true for the limit as well. So you couldn't have a net or sequence, well, net you should really use, of characters which are all taking the value 1 at the identity element 1, they couldn't converge to something which didn't take the value 1 at the identity element 1. That sort of thing. You don't have to use nets, or you can't use sequences. That's not enough. But you can base your idea on that. The fact that you know that all the things are going to have to take the value 1 at the identity element is going to stop the zero multiplicative linear functional from being in the closure. Okay, evaluation characters. You've always got these available if you're dealing with complex valued functions on a non-empty set. So what happens here? Your algebra may be, for example, C of x. This is a typical example. It could be a compact Hausdorff space x, and you're dealing with C of x at Banach algebra. Then for each point of x, you get a character corresponding to a valuation at that point. And as we know, if I use a hat, that means evaluate at me. So x hat is defined at f to be f of x. Now this is not any more to do with the dual space of a norm space, because x is just a topological space now, usually. There's no linear structure anymore. So it's different from, but similar to, the notion of hat we had before about being evaluated at me. But now it's evaluated at a point of a set, which isn't necessarily anymore got any linear structure. It probably hasn't. There's another notation for this. You can also use epsilon sub x. So the evaluation character is often written as epsilon sub x. So epsilon x of f, again, that's evaluate at me, so that's f of x. So it's just an alternative notation. So that gives you quite a lot of, if you're dealing with algebras of functions, that gives you quite a few characters, but in general there may be others. However, it turns out, though, we won't prove this, for C of x, there aren't any others. So it turns out that the only characters you can have on C of x for a compact Hausdorff space x are the evaluations at points of x. So not only does that give you a good supply, that's actually all of them. And that's true for some other situations as well. It's true for R of x, which is not too hard. It's true for A of x, which is very, very hard to prove. There's a bit of deep theory in that. R of x I could probably prove for you given another half lecture. A of x would take a large portion of another lecture course. Oh, okay, that's an exaggeration, but it's quite significant. Deep theorem. And P of x, it isn't true. Similar problems as before. If you've got holes in your space x, it stops P of x having the right set of characters. You get extra characters corresponding to points in the holes when it comes to P of x. So that's like before. Details in books if you're interested. So that brings us on to, not everyone agrees with me on this one. I think of this as a fundamental theorem of Banach algebras, but some people would say this is too elementary to deserve that name. It's the first surprising result about Banach algebras, that characters are always continuous on Banach algebras. Not only that, the norm of a character is always at most 1. When you're dealing with a unital, you get equals 1. If it's non-unital, you just get less than or equals 1. So, well, to prove this, first I want to have some preliminary discussion. So our target is to do 2.4, but I want a little bit of preliminary discussion first. So preliminary discussion relating to Theorem 2.4. So let A be a commutative unital, or a commutative unital complex algebra just for the moment. So I just mean a complex algebra with an identity, but it may as well be a Banach algebra for this discussion. So I just mean it's got an identity so far. If it's a Banach algebra, then unital means also that the norm of 1 is 1. For a character phi on A, we know from the discussion above, phi of 1 equals 1. Now, suppose you've got an invertible element. And we'll set b equals a to the minus 1. Then 1 is equal to phi of 1 is equal to phi of ab. B is a to the minus 1. That's equal to phi of a, phi of b. So what can you tell me? If you've got two complex numbers and they multiply together to give 1, what does that tell you they can't be? Can't be 0, right? So, in particular, phi of a is not equal to 0. So what do we prove? If you've got an invertible element and you've got a character, then no, phi of a can't be 0. And that's what we're going to use to prove theorem 2.4. So phi of a is not equal to 0 for all a in of your algebra. And now we use this to prove theorem 2.4. So what have we got? We've got so A is now a commutative unital Banach algebra. And phi is in the character space. So phi is a non-zero multiplicative linear functional. We know phi of 1 is equal to 1. That's a good start. So that's going to tell us, once we've shown that phi is continuous, that the operator norm is at least 1. So we can prove the rest of it if we can only show that the modulus of phi of a is always less than or equal to the norm of a for every a in the algebra. So the result will follow if we can prove that the modulus of phi of a is less than or equal to the norm of a for all a in A. Because if you get that, then it's a bounded linear functional and the operator norm is at most 1. So that would give you bounded with operator norm at most 1. And then this one tells the operator norm is at least 1, and you get the rest. I will remind you of that at the end, though, with a sort of optional extra bit at the end to finish it. Okay, so we'll suppose for contradiction that's not true. Suppose for contradiction, and remember, we only know algebraic stuff about phi at the moment. We don't know it's continuous yet. So we'll just suppose for contradiction that a in A satisfies modulus of phi of A is greater than the norm of A. Well, then note that phi of 1 over phi of A is 1. Okay, just multiply A by the complex number 1 over phi of A, which of course is not 0 since it's greater than something, the modulus, so it's not the 0, so that's okay, is equal to 1. So let's set x equals 1 over phi of A. Phi of 1 equals 1, and norm x is 1 over mod phi of A times the norm of A, which, by our assumption, is less than 1. Now, what did we prove about elements of Banach algebras with norm less than 1? If x has got norm less than 1, what did we just prove a little while back about elements of Banach algebras whose norm is strictly less than 1? What can you do with it? It's not that it's invertible, because of course 0 would have that, but something's invertible. Can you remember what's invertible? The idea is if you're within one of the identity element, then you'll be invertible. So it's not that x is invertible. What was that series we had before? 1 plus x squared and so on. That was the inverse for which element? 1 plus x squared and so on is the inverse of which element? 1 minus x, exactly. So 1 minus x is in A. But what's phi of 1 minus x? It's phi of 1 minus phi of x. What's phi of 1? 1. What's phi of x? Oh, what have I written here? I wanted to say phi of x. I definitely wanted to say that phi of x equals 1, not phi of 1 equals 1. Though they're both true. Phi of x is 1. Phi of 1 is 1. So this is naught. So I have some sort of contradiction. What's my contradiction? Sorry? Yes, I've got an invertible element, and phi of it is 0. So this is impossible because 1 minus x is invertible. 1 minus x is invertible, and the character applied to it is 0. That can't happen. Is impossible, since 1 minus x is invertible. So that contradiction shows that there is no such A. And we've proven that modulus of phi of A is less root of the norm of A for all A and A. And I'll just finish it off again. I mean, I've already said why this follows. So that shows that phi is bounded, a bounded linear functional. And the operator norm of phi is at most 1. But phi of 1 equals 1 shows that the operator norm is actually equal to 1. Remembering that the norm of 1 is 1. And we've finished. So I think that's a great fact. Just from being a character, being multiplicative linear functional in Banach algebra, you automatically have to be continuous. Not true for normed algebras. There are loads of discontinuous characters in general. There are loads of discontinuous characters on normed algebras. So we've proven Theorem 2.4. And now, you put this together with the Banach Algebras theorem. We now know that the character space is contained in the closed unit ball of the dual. Remember. Okay, don't worry. So let's just have a look at this. We have VA is closed in C to the A, we mentioned earlier, and it's a subset of the ball in the dual, the closed ball radius 1, and we know that's weak star compact. So it's a weak star, it's actually a weak star closed subset of a weak star compact set. So it's a closed subset, is a closed subset of a compact space. Because you're using the weak star topology, not the norm topology here. And that is the topology, when you're studying Banach algebras, you usually use that topology on the space. It's called the Gelfand topology, and that's the one that's most useful when you're working with the character space. Any questions about what we've proved so far today? So, of course, what you do is you take the weak star topology, and then you've got this compact subset. So you do the subspace topology. That's called the Gelfand topology, as I just said. And as usual, it's got this characterization. It's the weakest topology making all of these evaluation maps continuous. In other words, that's a hat. So it's the weakest topology such that all the A hats restricted to VA. All the A hat, oh, let's get this right. It is true, restricted to VA are continuous. That's the old A hat from earlier. Unfortunately, we're about to have another A hat coming up in a minute. Mostly, which is, this restriction is often also denoted by A hat and called the Gelfand transform. Unfortunately, we won't have time to prove that there's always at least one character, but that's in a bit of later theory. But it is true that if you've got a commutative unital Banach algebra, there is always at least one character. Sometimes there's only one, but I say we'll return to it later, but we won't actually have time to come back to that. So you'll need to, that's an optional reading exercise to find out a bit more. So this Gelfand transform is, as I said, it's the old A hat restricted to the character space. As I said, it's got two different things. There's Gelfand transform is used for various different things. It's used for the map from A to the continuous functions on the character space, which takes each A to A hat, but that's the old A hat restricted to phi A, which we now, it's still evaluate at me, but it's only defined on the characters instead of on all the functionals. So the map is called the Gelfand transform. A hat is called the Gelfand transform of A, and the Gelfand transform of the whole space is called ahat. And it's only a bit of a clash because you're restricting the previous ahat to the character space instead of working on the whole dual space. But it's pretty much the same thing. So if you see a hat, you need to work out whether you're talking at the moment about embedding A in A double star, or whether you're talking about commutative Banach algebras and finding a continuous function defined on the character space. So we'll finish with a brief discussion of semi-simple algebras. Now there's lots of different definitions of semi-simple around, and ring theory has its own definition, and you can define it in terms of maximal ideals or maximal one-sided ideals and so on. We'll give a definition in terms of characters which turns out to be equivalent to the usual one once you know a bit of theory. But I just wanted to give you the one that's easiest for you to work with. So there is an algebraic definition, and you can look in the books if you want to see why this is equivalent to the usual definition. So for us, what we do is you look at the kernels of the characters, you intersect over all the characters, you intersect the kernels, and of course 0 is in every kernel. The intersection of these kernels will be some subspace of A. In fact, it turns out to be what they call an ideal. And the intersection is called the Jacobson radical, but we don't have to worry about that. Well, so that's semi-simple if the intersection of all the kernels has just got 0 in. In other words, that means that if you've got a non-zero element of A, there has to be a character that doesn't kill it. Right? So this is true for some algebras and not for others. There are, for example, if A squared is 0, but A isn't, then this doesn't happen. And I've given you some examples already of commutative Banach algebras where there are some elements whose square is 0. So typically, if you're dealing with functions, you're absolutely fine. And if you're not dealing with functions, then it's possible to have an element whose square is 0, and that will mess you up. It's not the only way of messing you up, but that's typically what you might think of happening. So let me say, so algebras of functions are always fine. That's because there are point evaluations around, and the point evaluations are enough to determine if point evaluations will be characters, evaluate at various points of your set, and if all of those characters are 0 at your function, that means the function is 0 at every point of the set, which means it's a 0 function. So use evaluation characters to see this. That's already enough. Now, it could be that there are some other characters as well, if you're dealing with an algebra of functions on a set. But since the evaluation characters are already enough to have kernels intersecting down to give you 0, if you intersect with a few more kernels, it's not going to change anything. It's still going to be 0. So you only need to find enough characters to get down to 0. And if there happen to be some more characters around as well, that just helps. I mean, well, it doesn't do any harm. So that's this comment here. You've got a unital Banach algebra of functions on a set. You just look at the evaluation character at the point of the x, and you do the intersection over x in your set x of the kernel of x hat is equal to f in A such that f of x equals 0 for all x in x, which is 0 already. And as I said, then that says that if you intersect some of the characters' kernels, then you get down to 0. If there happen to be some more characters around, it doesn't do any harm. Now, the interesting thing is that if you've got a semi-simple commutative unital Banach algebra, then it is, in fact, an algebra of functions on some compact space, up to isomorphism. Because if you look at what the kernel of the Gelfand transform is, it's the intersection of the characters. The kernel of the characters. So that Gelfand transform map, let's say the kernel of hat is equal to the intersection over phi in the character space of the kernel of phi. So if that intersection is 0, that hat is the Gelfand transform map. And the intersection then, the kernel is the intersection of the kernels of characters. If that's 0, then this map is injective, and that means that your algebra is isomorphic to its image. And so you can just work with a hat, but a hat is an algebra of functions. A hat, that's the set of evaluate at me functions defined on the character space, VA. And I'll leave it to you to work out what an algebra homomorphism and an algebra isomorphism are. Well, it says here, a multiplicative linear map is an algebra homomorphism. A unital algebra homomorphism is an algebra homomorphism that takes 1 to 1. So this also has that property. And bijective algebra homomorphisms are algebra isomorphisms. So just to discuss the last results at the end of this section, what's a unital algebra homomorphism? As I said, that's one that takes the identity element of one algebra to the identity element of the other. And here's a very nice automatic continuity result, which you can see on the question sheets. And it comes from the closed graph theorem and the continuity of characters. So it uses the closed graph theorem and continuity of characters. And this is a boosted up automatic continuity result. We already have a special case of this that says that characters are always continuous. And now, Theorem 3.3 says that every unital algebra homomorphism from a commutative unital Banach algebra into a semi-simple commutative Banach algebra is automatically continuous. So if you map, if you've got just an algebra homomorphism, well, unital algebra homomorphism, and it maps some commutative Banach algebra A into a commutative semi-simple Banach algebra B, then it has to be continuous. It can't avoid it. And that's a very powerful automatic continuity result, which is relatively easy in the commutative case. There's a version in the non-commutative setting, not quite in, you need a bit more information, but it's much, much deeper. So the non-commutative version is much harder, and moreover, you need to assume then that the homomorphism is onto. But you get this nice uniqueness of norm result that means, suppose you've got a semi-simple commutative unital Banach algebra. Think of it as a Banach algebra of functions, maybe, on some compact Hausdorff space. And suppose you find another norm that also makes it into a commutative unital Banach algebra. You might have thought you could find a completely different one. But it turns out not. They have to be equivalent. So if you've got a commutative unital semi-simple Banach algebra, if you've got a commutative unital semi-simple algebra, it's always got at most one Banach algebra norm on it, up to equivalence of norms. So it's a uniqueness of Banach algebra topology. So you can think of this as uniqueness of Banach algebra topology. It's not saying that the norms are all exactly the same. You can mess around and get slightly different ones. For example, on finite dimensional algebras, like C to the n, you could mess around a bit with the norms and find various different Banach algebra norms, but it's not going to change the topology. And the same goes for any old commutative, semi-simple, unital Banach algebra. And that is the end of the examinable material. There's some interesting stuff in here which is optional reading material, but I just leave it to you if you want to look at that or at the books, to give you a little bit more of a flavour of what Banach algebras is about. But we finished the examinable material now. So it remains this afternoon to look at the measure theory, and then we'll have a question and answer session at the beginning of next term, and we'll see what questions people come up with over the holiday. But we'll stop for there for this session.